record. Share. Okay. If we look at the attendance, you said Tuesday, right?
Yes, ma'am.
Okay. Suppose a person has a retirement investment. Oh, I forget what day we did these. Okay, now it's up to you if you want to do it algebraically or graphically. I'll show both because I think on the test I'm going to have you do both. That way I know you understand how to use Desmos and how to do the algebra. But these are simple interest. In a retirement, she intends to withdraw $36,000. There we go. Now, when you're talking about simple interest, you can use I equals PRT. This is a formula that you could have on a formula sheet. And last class, if you weren't here, we discussed using your notes, which is fine. But sometimes when you use your notes, it takes a lot more time to do a problem and you will not be able to get done. So have a formula sheet. That way, then the ones you know, you still have that formula there to look back on. But if you need to look up a problem, then you could do that also. Okay, let's see. So what's happening is she wants her interest that goes into the account to be the same as her withdraw.
You know how to do it from your lab.
No, the withdraw is the 36,000.
Okay.
Going in is the interest, which was 6.5%. No, it's 6.5% of whatever's in here, which usually they use a capital P for principal, but you could use any variable you want. In fact, if we wanted, we could use an X. But this is the amount in the account at any time. So we want what's going in to equal what's going out. Now, when you're using a rate, you need to rewrite it as a decimal. And it's this percent of what's in there. Of means to multiply. So this is what would be going into the account. In this formula, T is just 1 because we're talking about each year.
Okay, that makes sense.
Now, to do it using algebra, we want this to equal this. You could just set them equal. Now, if we were going to solve this, how would we get P by itself? Anyone?
Divide each side by 0.065.
Yep. Because we want to get rid of this decimal. It's being multiplied. We can divide it. You're getting, wow, 553,000 and some.
Definitely keep that because that's what goes wrong. That's like something.
Now, if we want to round to the nearest dollar, you would round up. Because if we take 6.5% of this, we're going to be a little short of the 36,000. So any rounding has to round up. Even if we rounded to the nearest cent, this would have to be a 16. If it doesn't specify, it's up to you where you round, but since it's money, you don't want to go further than cents. I probably will say round properly to the nearest dollar, so it kind of helps you remember that you should round up.
Okay, thank you so much.
You're welcome. Are you okay doing it graphically?
I think now that I understand the algebra, I think I'll be able to figure it out.
Okay. Let me just in case someone else. For the graph, take this side, y equals 0.065, but then instead of p, use x because that's what Desmos uses, x and y. And then this one would be y equals 36,000, and then just find where they intersect. Any questions on that? Does anyone need me to do the graph?
I wouldn't mind seeing it done on the graph just real quick, like.
Sure, no problem.
Not trying to take away from time in class.
Not a problem at all. I want to make sure everyone understands it. I mean, if we have to not finish the chapter, then we don't finish the chapter and we take a test on what we got. No, we'll go at whatever speed you need. And yes, I will go over Wednesdays also. Okay, so for the graph, because I want you to be able to do this, this is kind of review for the test. So make sure you make a note that you want to study it for the test. Put Desmos on this one. So go to desmos.com and then click on graphing calculator. Sorry, I'm losing my voice today. And then you would write these two equations. So I just took them from this first part and I made P and X only because that's what graphing usually uses, X and Y's. I tried doing it with a P to see if we could, and it was giving me weird values. So you just type both equations. No, it's only showing my red line. Well, look how low my numbers are. That's why. So you want to zoom out until you find it. You could also use the wrench and put in values, but when we don't have a table, it's just guessing. So it's better to just keep going. Now I see both lines, so I'm going to move it till I see where they intersect.
I think I was getting confused with the graph because I was doing like a y, like for the 6.5, but then I was also trying to do an x for 36,000 to make them on opposite sides of the graph. So I think I was confusing myself.
I could see that. And here, let me open this up so you could see more. The reason you don't want the X with the 36,000, it's constant. We are always taking that out. Doesn't matter. It's always constant. So that's the horizontal line. Now, when you want to see where they intersect, you can click any one of the lines. Like if I click even over here, notice it showed me where they intersect. So if they're still a little close and it's hard to see exactly, as long as you only hit it once, it will show you where they intersect. And then if you click it again, it'll stay on there. So then when you take your picture, you take your picture of this whole screen so that I can see the equations, the line, and the intersection. And then see, this is 553,847, which is what we wrote down.
Thank you again.
You're welcome. Any other questions on this one? Okay. Um, So that was Tuesdays. Each spring, the porcupine caribou herd migrates to its calving grounds in the Arctic coastal plains, northwestern Canada. 36,000 surviving calves are added to the herd if the average residence time for a caribou is 5 years, and assuming the herd size is at an equilibrium. What's the size of the herd? So we know we have calves that are going into the herd. And we said it was 36,000. Now it's saying they're only staying in here for 5 years. So coming and going out. Probably. I wouldn't think they'd leave the herd, but it could be death, it could be leave herd. So for any certain reasons, 36,000 go in and 36,000 go out, and it said that the residence time was 5. So that means at any time, like these calves going in, they'll last for 5 years and then they're no longer in the herd. We want to find out how large the herd is. I gave the formula, so it's residence time equals the level of the stock. Level of stock would be the size of your herd. And the flow rate is how many are going in and out. So 36,000. What happens is if these are not at an equilibrium, then the herd gets too large or it gets too small. And so this would tell us now our residual time said was 5. We're looking for the size of the herd. We could use H for herd or C for caribou. And then the flow rate, that's your 36,000. So however many are coming in and going out, that's your flow rate. Residence time is how long they reside in the herd. And then size of the herd would be on top. This is a formula I'd probably write down so you have it. Any questions on setting it up? How would I solve it?
Multiplying each side by 36,000.
Yep, because we're dividing here to get rid of it, we multiply both sides by the 36,000. Getting 180,000. So questions like this is what I will ask on your exam, like the last one that we did and this one. And you'll have the formulas.
How many questions is the exam gonna be?
I have no idea. I haven't started it. Usually my exams have 13 problems. I don't know, I like the number 13. And I find that if there are questions like this, 13 problems, 50 minutes should be easy. I don't think, like in my stats classes, I have maybe 5 problems, but then they're like A, B, and C because I have the steps to build, but I don't think we're really, other than maybe scientific notation or something, we're really not gonna have. I'm trying to stay with the more basic problems. So they more than likely will not have multiple parts. Maybe one of them will. So probably 10 to 13 problems. But I will make the test hopefully tonight, and an outline will be up by Sunday morning. Any other questions?
Thank you for helping.
Oh, you're welcome. I don't mind at all. Anytime you have questions on the homework or the attendance problems, let me know. I know they're getting a little more involved since I'm not giving a homework set of problems. I thought one each time, and these are good problems to study for your exam. Any other questions? Okay. We were almost done. Whoops. With 2.3. This stuff is not cooperating. Come on. It's like right in the way, so I can't drag it. There were, I think, 2 problems that I wanted to do in this section that we hadn't done yet. Oops, problem 6 is where we were. Now, the rate of heat loss, there's a formula here. The delta T is just your outside temperature minus your inside temperature. Area of whatever wall we're talking about, ceiling, floor, it's just the area. Usually length times width because it'll be a rectangle, or like this one, they gave us the area. And then 1 over the R value. Remember, the R value is a measurement of the resistance, the thermal resistance, but it's the heat that's staying in the house, or the cold air coming in, or vice versa if you have air conditioning on. But it's a rating for that insulation. So if we have an exterior wall in a particular house is 160 feet squared, so they're giving us the area, and has an R value of 12, and don't worry about it. The measurements are just so you can cancel and see what measurements are left, but it's hours, degree Fahrenheit, feet squared divided by BTUs. Calculate the rate of heat loss when the indoor temperature is 70 and the outdoor temperature is 40. Okay, So if we look at the formula. Heat loss. Shrink this a little more. Equals, I'll write it down first. The change in T times area times 1 over the R value. Now, if you wanted, you could just put R value underneath this because you're dividing. So this could also be written. It's the same thing. The reason they did it separately was because then the units get all pushed together. But they're all on the bottom, so I don't know that it would matter. So you could write it like this, or you could write it like this. Same thing. Delta T is the difference in your temperatures. You just subtract them. So it's 70, what did they say it was? 70 was inside and 40 was outside. So it's 70 minus 40. The area was 160. Now, if you want the units, we could put them. This was, oops, degrees Fahrenheit. This one's 160 feet squared. Yeah. Now, the units here, notice they are also feet squared. So if they gave us something else, we'd have to change units to feet squared. But since the R value is also in feet squared. So it's 12 hours, degree Fahrenheit, feet squared per BTU. The reason they show the units is notice that the degrees Fahrenheit cancel, feet squared cancel, and then we'll have BTUs per hour left. Any questions? If you calculate the numbers, this would be 30 times 160 divided by 12. You should get 400. Everyone getting the 400? Now, this BTUs, because the division, I wanted to show you how it becomes 400 BTUs per hour. Because this is in the denominator of the denominator, we can multiply by BTU over BTU. These two will cancel and leave 400 BTUs per hour. Or you can think of it as flipping the bottom fraction and multiplying. When you're dividing by a fraction, you can flip it and multiply. And you're just flipping this. Any questions on that? So that's our answer. The biggest thing is making sure you know delta T is just change in temperature. Area was given and R value. So this is how much heat is being lost in this home just from that one wall. Any questions on that? The outside temperature plays an important part in our home heating model. You might wonder, though, how it fits into the structure of system diagrams, as we have been discussing them so far. The outside temperature is not a stock or a flow in the model, but it's nevertheless an influence on how the model works, because notice if this got colder, then this value would be, instead of 30, it'd be a lot higher. Say this was 20 degrees outside. And then this would be 50 that we're multiplying in here, and that would make this a lot higher. So that outside temperature plays a large part, but it's not really a stock in the model. They call it a parameter. A parameter in a stock flow model is a quantity that is not itself a stock or a flow, but that affects it. So it affects the flow rate. It cools down the house, has to work harder, and has an effect on the amount escaping. Any questions on that? So even though that outside temperature wasn't part of the flow, it still affects it. If you have insulation with an R value of 15 and add another insulation on top of that with an R value of 20, what's the combined R value? Now there's a thing in your book and it's probably 2.5 pages of work proving this. I don't think we need to prove it for this class. But if you want to look at it, you can. But the R value of 15, if you're putting another R value right on top of it, not removing, but putting on top, so you have more insulation, you actually can add those together. So if you have an R value 15 and add an R value of 20, the R rating for your house then will be 35. At least in those areas, if it's not everywhere. But so if you put one on top of the other, it actually is added together. Any questions on that? I guess this is one that I could put a 2-part, like you would solve this problem. Yeah, they had a 12 rating. And then I could ask if you decided, because it's losing so much, to put another insulation of an R value of 20, what will your new R value be? Then you would add them together. Any questions on that? So if you have an insulation, you put another one, you can add their R values together to get your rating. Any questions?
I thought the R value was 10, not 15.
For this problem,
Oh, well, on the section 2.3 that was on the that as you learn, when I clicked it, it has the floor has a poorly insulated attic has an R value of 10 hours.
Okay, I must have switched.
Oh,
I
okay.
forget why I switched it because something else we did had those two and but that's okay. Yeah, if this is a 10, then what would it be?
Okay. Yeah. 10.
Yeah.
Hmm.
I forget that there was something like that problem. And so then I switched it to a 15, but I thought I changed it, but maybe you looked at it before I switched it also. Yes, so if this is a 10, then it would be 30.
Also on the test, are we gonna have to write degrees feet squared over BTU, or can we just write like the number?
You can just write the number for right now, at least this exam. I just want to see where you are mathematically, so then I know how much more difficult the math parts can be. So we won't worry. I'm not too worried about the units right now. I think the units help you know that you did it correctly though. But yeah, I'm not too worried about the units. Any other questions? So if your outline when you opened it has a 10 here, the answer would be 30. Any questions on that? And then R value does not, let me make sure. I believe the R value does not have a rating. I mean, a unit. R values do not have units. Yeah. Any other questions? I don't know why that one's set so big. There we go. Section 2.4. This section talks about energy flow and climate change, the greenhouse effect. The Intergovernmental Panel on Climate Change, you'll see the initials throughout the book, IPCC. That's what it is. It's a panel that was set up in 1988 to help inform people of how the climate is changing, basically. Over the past quarter century, they've attempted to inform the world community about unexpected sustainability risks, carbon dioxide, recycling. They had a play in that. But the main thing that's changing is the Earth's climate. And yesterday it was 70 degrees here, and today we have a high of 32. I'm sure climate change has something to do with that.
Yeah,
So
on Wednesday it was like 60 degrees here, and now it's gonna snow like a 80 to 100% chance on Sunday.
Yeah, see, and that's probably why my throat is like this. My system doesn't like when it goes back and forth.
Mine either. I just got over being sick for like a week.
Oh, wow. Yeah. So it's just like, um, I don't like this. For February to be 70, I don't know, what's it gonna be this summer, 90, 100? Um, I wouldn't complain, that would be good though. We haven't had much bad weather here, like maybe 5 days where it was snow or cold. And that has a lot to do with climate change. A summary for policymakers in the 5th assessment report. It said continued emissions of greenhouse gases will cause further warming and long-lasting changes. All components of the climate system increase the likelihood of severe, pervasive, and irreversible impacts of people and the ecosystem. Limiting climate change would require sustainable, substantial and sustained reductions in greenhouse gas emissions. Now, what we're going to learn though, also, in some of the problems we're going to do, we need greenhouse effect because that holds in the heat, but we can't overdo the greenhouse effect or we won't survive. So without the greenhouse, we also would not survive because it would be so cold. And that's what you'll learn in this section. Now, when you think about them trying to predict the future, and they're explaining here, there's a difference in the word climate and weather. Climate is over time. Weather is right now. And I know that when I want to see what the weather's going to be in the week or two, I only trust the first 3 days. I always said the weatherman has the perfect job because he doesn't have to be right. But climate is over time, over a long period of time. What patterns are we seeing? And so we can be a little bit more accurate. We can show the changes over time, where weather is in the now, and it does change very quickly. Climate, of course, comprises many factors. 2 of the most important ones are the effect on our agriculture or production and surface temperatures, the air measured by a thermometer, precipitation, and rainfall. I forget how much it was. My son did an experiment one time when we had a snowstorm, and he filled a pot with snow and then let it melt and compared the snow to how much water was left, so that you could see how much snowfall would be it would take to get an inch of rain. And it all depends on how heavy the snow is. And so but we do need so much precipitation, or we're in what they call a drought. Energy transmitted by electromagnetic radiation is called radiant energy. Electromagnetic energy comes in many different forms: radio waves, microwaves, infrared, ordinary light, ultraviolet, X-rays. These are all examples of electromagnetic radiation. They're wavelengths. Important part, like a wavelength just goes like this. And what they do to measure a wavelength is they go from the tops, the crest, they measure the distances. The hotter objects have shorter wavelength and they're bluer in color. The cooler ones have longer wavelengths. But a wavelength is measured by its peaks and not how high it goes. There are several ways that radiant energy may be generated, but only one is relevant to climate discussion, and this is the heat or thermal radiation. Thermal radiation is the radiant energy emitted by a physical object when it is heated. And I'm not going to ask you definitions on the test. It's just so that we know when we're reading a problem what things mean. So thermal radiation is the heat. Stefan's law, the amount of thermal radiation emitted by each square meter. So it's only talking about, well, a meter is like a yard for the surface area. They do it in temperature Kelvin. So T is the temperature and kelvins is our measurement. They use sigma T to the fourth. This is the formula for heat. For thermal radiation. So that's a formula we'll use when we want to find the thermal radiation, or if we're given that, we can find the temperature. This sigma is a constant, and it will always be, unless there's a different problem set up, but it will, according to Stephen's law, it will always be this. So your sigma is now this is a -8 in the exponent, so be careful. So right here is a -8. And then this is just units, watts per meter squared, Kelvin to the fourth. And that Greek symbol is sigma. An idolized physical object in the sense is also called a black body. And Stephen's law is also called black body radiation law. In case you look up anything, you may see that. Most condensed matter, solids, liquids, follow this law to a reasonable accuracy. So when we're talking about finding an object's thermal radiation, unless otherwise stated in the problem, everything should have this sigma, 5.7 times 10 to the -8. The Earth's climate results from an equilibrium between incoming radiant energy from the sun and outgoing radiant energy from the warmth of the Earth. So we have heat coming from the sun and the warmth from the Earth. Time is it? We'll do this one problem. The sun is modeled by a sphere, and this is its radius, and surface temperature 5,800 kelvins. What is the thermal power output of the sun according to Stephen's law? So remember, our thermal radiation is sigma T to the fourth. And according to Stephen's law, we know what sigma is. It's the 5.7 times 10 to the -8. And then the temperature, they gave us right here, 5,800. And just multiply it out. Now here you're taking this number to the fourth. So it's gonna get huge, and then you're gonna multiply it times this. I got 6.441 times 10 to the 7. Now this is going to be k to the fourth, and k to the fourth cancel, so this would be watts per meter squared. Any questions on that? No, this is only for a meter squared. We would need to find the whole surface area of the sun, which is a sphere, to convert it, because that's only 1 meter squared on the sun. But any questions on finding this value? So this is only per meter squared. The surface area of the sun is this. So we would need to multiply these both together to find the total heat that the sun gives. So if you search for surface area of sun, this is what you're going to get. Multiplying these together then will give us the watts, because this is also meters squared. I think it was meters squared. Yeah. Because our meter squared will cancel. And leave just watts. So that's the number of watts, or yeah, that it is emitting. You should get around 3.97 times 10 to the 26. So that's how much heat the sun is emitting or sending us. Any questions on that? Positive. So this was just giving us a small area on the sun. That's why we found the surface area and then multiplied them together so we could get the entire heat from the whole sun. Any questions on that? Okay, if you do not have any questions, I will see you on Monday.
Thank you.
You're welcome. Have a nice day.
Take care now.